Hi, we're going to look at lesson 2 today, which is Introductory Differential Equations. This is continuing on from our study of implicit differentiation in lesson 1. So in this lesson, we're going to solve simple first order differential equations of the form dy dx equals fx or gy or fx gy. In that case, you have to use separation of variables. We're also going to use implicit differentiation to determine gradients of curves defined implicitly. An ordinary differential equation is an equation involving x, y, and various derivatives of y. Some examples are shown below. So here we have dy dx equals negative sine x. We have dy dx plus 2y plus 5 equals 0. We have derivatives with the second derivative, d squared y over dx squared. And we have different varieties here. Now the order of the differential equation is the order of the highest order derivative of y appearing in the equation. So here's the highest order here, whereas in this equation here, the highest order would be the second derivative over the first derivative. Equations 1 and 2 are first order, 3 and 4 are second order, and 5 is third order. In this unit, we discuss only differential equations of degree 1. A linear differential equation is one in which all variables, including derivatives, are raised to the power of 1. Equations 1, 2, and 5 are linear differential equations. Classifying solutions to differential equations. The solution of a differential equation is a clear definition of the function or relation without any derivatives involved. So for example, if we have the differential equation here, dy dx equals 12x squared, and by solving this, we could perform integration techniques of the 12x squared dx to produce y equaling 4x cubed plus c, where c is the constant of integration. This is an example of a general solution to the differential equation dy dx equals 12x squared. A particular solution is obtained when some other initial value condition is known. This enables you to find the constant of integration. Verifying a solution. Example 6. Verify that y equals e to the 5x is a solution of the differential equation dy dx plus 3y equals 8e to the 5x. We're going to let y equal e to the 5x. Hence dy dx equals 5e to the 5x. On the left-hand side, we have dy dx plus 3y. Now dy dx we know as being 5e to the 5x, and y is e to the 5x. So by substituting those in, we have 5e to the 5x plus 3 lots of e to the 5x. Hence we have 8e to the 5x, which equals my right-hand side. Hence we validated or verified that it is the solution. Example 7. Show that x squared take x cubed y plus 3y to the 4 equals c is an implicit solution for the following differential equation. So what we want to do is differentiate this. So using implicit differentiation in terms of x, we're deriving it. So d dx of x squared, because we have a product here with the negative x cubed y, our u and our v, using the product rule, be u v dash plus v u dash. And implicitly differentiating here, we have our d dy of y to the 4 dy dx, and a constant when we differentiate, it's going to become 0. So d dx of x squared is 2x. We've then determined u v dash and so on. The next step is to remove this brackets, so we're going to subtract this and also subtract this. From here, we're going to solve for dy dx. Let's isolate dy dx. So we're going to subtract 2x from both sides and add 3x squared y to both sides. We've also factorized dy dx outside those two terms. To then isolate or solve for dy dx, I can then divide both sides by negative x cubed plus 12y cubed. And hence, we've shown that this is an implicit solution of the following differential equation. Last step here, I just rearranged it so it looks a bit more explicitly like this one up here in terms of writing it as 3x squared y take 2x, and similarly 12y cubed take the x cubed. Not entirely necessary, but just to be particular about it, we just did it as one more step. Therefore, that equals my right-hand side, and we're shown. So that's the end of our lesson 2, which is introductory differential equations. So you can now test your knowledge by verifying that y equals x e to the negative x cubed is a solution of the differential equation shown here. So test that one out and see how you go. All the best.